If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. This is March 2024 Common Test. Here we go. So let's go ahead and take a look at 1.1. The diagram below shows a woman at a shooting range. The woman fires at a target in front of her and immediately involuntarily sways backwards due to the shot taken. Which physics law can be used to explain why the woman sways backwards after taking a shot? Right, so, well, let's go through the basics. The woman fires a shot and then she sways backwards, right? So there goes the shot and the woman sways backwards. Why is the woman swaying backwards? Action, reaction, pass, right? There's a force forward, so there must be an equal force in the opposite direction backwards. That's why the woman sways backwards, right? So the bullet goes off the gun. There's a force in the forward direction, but the gun is gonna recoil, hence the woman sways backwards. So that is explained by Newton's third law of motion. So the answer to 1.1 is C, right? We can explain that using Newton's third law of motion. When body A exert a force on body B will exert a force on body A of equal magnitude but in the opposite direction, right? That is 1.1. Let's take a look at 1.2. 1.2, a 10-gram tennis ball traveling at velocity 2v to the right strikes the wall and bounces with velocity v as shown below. The vector diagram not drawn to scale representing the initial, final and changing momentum of the ball is indicated below with letters x, y and z. Which of the vectors x, y and z represents the final momentum of the tennis ball? Let's go and figure that out. The options that we have is A, B, C and D, where we have x, y, z, and D says both x and y. So let's take a look at what's happening, right? So it's the vector diagram showing the initial, final and changing momentum. So what is the initial momentum, right? As the object is moving towards the wall, it is mass multiplied by the velocity. Let's just put mass in place of, let's just put m in place of the mass, and then velocity, let's substitute 2v. So the initial momentum is equals to 2mv. Okay, let's take a look at the final momentum. So p final, let's take direction to the right as positive, or direction towards the wall. So the mass of the object is still m, right? But then now the velocity is minus v because you're taking direction towards the wall as positive. So p final is minus mv, right? Let's have the change in momentum. So the change in momentum is equals to the final momentum minus the initial momentum, right? Minus pi. So this is going to be equals to minus mv minus 2mv, which is equals to minus 3mv. So this is what we are expecting. The initial momentum, if we're taking direction to the east as positive, should look something like that. So that is about 1, 2, 3. Let's just make it 4 centimeters. Yeah, so this is the initial momentum, right? And then what about the final momentum? The initial momentum is 2mv. The final momentum is minus mv. So we'd expect that to be about 2 centimeters. So this is the final momentum. What about the change? The change is minus 3 mv, minus 3 mv. So we would expect the change to be way greater than the final and just a little bit greater than the initial. So this is the change, about 6 centimeters. So yeah, that's about it. So this is the change in momentum. This is the final. This is the initial, if we take east as positive. So let's go back to our question and see which answer we can go with. Okay, so the vector diagram not drawn to scale representing the initial, final, and change in momentum of the ball is indicated below with letters X, Y, and Z. Which of the vectors X, Y, and Z represent the final momentum of the tennis ball? So the final momentum of the tennis ball should be the smallest vector of the three, which we can clearly see that that is Y, right? It points to the left and it's smallest and is the smallest in size. So the answer to 1.2 is B. Okay, let's take a look at 1.3. A bus with mass 5m collides head-on with a car of mass m. The bus experiences a change in momentum of x kg meters per second east due to the collision with the car. What is the change in momentum experienced with the car due to the collision with the bus? Okay, the change in momentum is going to be the same, but in the opposite direction, right? Okay, so what options says that? It is option B. So the answer to 1.3 is B. But wait a minute, let's go through it. Why is the answer B? Why is the change in momentum the same? Take a look at this. We have the force that the bus exerts on the car, right? So let's say FBC. This is equals to minus the force that the car exerts on the bus. Would we agree with that? Yes, you would agree. Newton's third law, right? But then what is force, net force in terms of momentum? That is delta P over delta T. So this is also equals to minus delta P over delta T, right? So the time of the collision as the two objects are colliding with each other should be the same. So you can clearly see that delta P is equals to minus delta P, right? So we can see that the change in momentum of two objects when they collide with each other, it should be the same, regardless of their size and regardless of their velocity. The change in momentum should be the same. Newton's third law, when we incorporate it with Newton's second law, it should be easy to see here. So that is why we are saying the momentum is the same, but in the opposite direction. Why we are going with option B for 1.3. Okay, let's go to 1.4. So 1.4, a velocity versus time graph describing the motion of a projectile is drawn below. Refer to the graph to answer question 1.4 and 1.5. Okay, which one of the following combinations is true for the direction of the initial motion and gravitational acceleration of this projectile? So let's take a look at our graph, right? After some time, our object reaches maximum height. We can see that because it has a maximum, it has a velocity of 0 at the maximum height. We know that it reaches maximum height because that's where the velocity can be 0, unless it is striking the ground and becoming stationary, which in this case, that's not the case, because if it was striking the ground and becoming stationary, then the velocity shouldn't carry on in that manner. Okay, so at this point, we know that our object is projected upwards, right? And then it reaches some maximum height, and then it starts going downwards. As to whether it goes downwards to the same height which it was projected, we're not so sure. But we know that it goes up to reach some maximum height and starts going down. So the first part of the question, initial motion of the projectile, we can answer that one. It is upwards. So already, the only options that you're looking at is A and C. We're looking at A and C, upwards and upwards. Let's talk about the gravitational acceleration of the object, right? Is it going to be plus 9.8 or minus 9.8? Well, that is going to depend on the direction that we are taking as positive, right? So let's take a look at our graph and decide which direction was taken as positive. So we're saying our object is projected upwards, right? But then the velocity starts off being negative. So what does that tell us? It tells us that down is taken as positive, right? We have taken downwards as positive. That's why an initial velocity, which is upwards, is negative in the graph. So if downwards is taken as positive, then the gravitational acceleration should be plus 9.8. So the answer to 1.4 is C. There we go. Let's take a look at 1.5. Which physical quantity can be calculated using the area under the graph? Okay, so which graph? The graph in 1.4. So this is a velocity time graph, right? So let's say maybe we want to find this area. What are we gonna say when we want to find that area? We're gonna say, well, half base multiplied by height, and then the base is gonna be the time, right? Here, so that is gonna be the time, and then the height is gonna be the velocity, right? So you can see that we have a product of a scalar and a vector. So when we have the product of a scalar and a vector, the resultant should be a vector, right? So C, not C, but A says speed. We know that is not true. We cannot multiply velocity and time and get speed. And then the velocity, we're multiplying the velocity by the time. How can we then get the velocity once more? Does it make sense? And then distance. The only issue with the distance is that distance is a scalar. So the answer to 1.5 is clearly D. Right, let's go. Let's take a look at 1.6. So 1.6, a ball is thrown towards the floor with velocity v from the top of a high building, thrown towards the floor. Right, okay. The contact time of the ball with the ground is negligible. Ignore the effects of air resistance. Which one of the following acceleration versus time graph represents the motion of the ball from the time it's thrown until it reaches a maximum height after it bounces off the floor? Upwards is taken as positive. So if upwards is taken as positive, the acceleration should be negative, right? So the answer to 1.6 should be B. That's the answer to 1.6, because if you take up as positive, the acceleration is negative. Whether the object is going up or the object is going down, the acceleration is going to be negative because you've taken up as positive. So that's why we're going with B as our answer, right? There is no such thing. This does not exist in free fall. The acceleration cannot change from plus 9.8 to minus 9.8 because of the ball bouncing or whatsoever. The acceleration is always downwards, right? And then whether it is positive or negative is going to be decided by whether we have taken up as positive or downwards as positive, right? So 1.6, the answer is B. The acceleration is always 9.8 meters per second squared downwards. The following is the structural formula of an organic molecule. Which one of the following is the correct IUPAC name of this molecule? Alright, so first things first, we're looking for the longest carbon chain, obviously. So 1, 2, 3, 4, 5. 1, 2, 3, 4. Actually 1, 2, 3, 4, not 1, 2, 3, 4, 5. So this can also be the longest chain, but we can just take the straight chain as it makes our life extremely easy. Okay, so when that is the longest chain, when we start numbering our carbons from the right, we have a branch on the first carbon and on the second carbon. And then when we start numbering from the left, we have a branch on the second carbon, the third and the fourth. So clearly we need to start numbering from the right. If you don't know why I'm saying that, check the link on my bio, join my course. It's absolutely free for the first 7 days and you will get all these basics. We'll leave no stone unturned. Right, so this is carbon number 1, 2, 3 and 4. Okay, so on the first carbon we're gonna have so this is 1.7. Let me just 1. What's happening to my pen? 1 point. Okay, let me just try fix what's happening. Just give me a sec. Okay, 1 point. Yeah, it's just all over the show. Okay, so 1.7, we have 1 bromo, obviously, right? That's one of the branch. The other branch is 2 chloro. That's the other branch. And the third branch is 3 methyl, right? And then 4 carbons. So that is butane. We have to arrange this in alphabetical order. So we're gonna have 1 dash bromo dash 2 chloro dash 3 methyl butane. That is A. So the answer to 1.7 is A. Right. Taking a look at 1.8. So 1.8 says that which one of the following combinations correctly indicates the strongest intermolecular forces found in ethanol, ethanoic acid, and ethyl ethanoate. So ethanol, alcohol, so it's hydrogen bond. So we still have option A, B, and C, right? And then ethanoic acid, hydrogen bond. So we have option B and C. And then ethyl ethanoate, that is an ester. The strongest intermolecular force is dipole. So that is option B. So the answer to 1.8 is B. Let's take a look at 1.9. 1.9 is just the definition of melting point, which is clearly D, right? Temperature at which the solid and liquid phases of a substance are at equilibrium. And 1.10, there's no such thing as 1.10, guys. It does not exist. There's only 1.10, right? And then when butane is subjected to high temperatures and pressures, the following reaction takes place. We have butane plus methane plus some organic compound Y, right? So let's make sense of what is happening. What is butane? Butane is C4H10, right? And then what is methane? Methane is CH4 plus Y. So how many carbons do we expect in Y? Here we have 4, here we only have 1. So we expect C3. We expect 3 carbons from Y. And then what about hydrogens? Here we have 10 hydrogens, here we have 4 hydrogens. So we expect 6 hydrogens, so that the total gives us 10, right? Because what's on the left must be on the right. So let's take a look at an option that corresponds with that. Should be easy to see that in option B, we have 3 carbons and 6 hydrogens. So 1.10, the answer is B. There we go. Okay. Question 2. 2 blocks P and Q resting on a rough horizontal surface are connected by a light inextensible string. The blocks have masses 5 kg and 2 kg respectively. A constant force F acting at an angle of 30 degrees to the horizontal is applied to the 5 kg block as shown in the diagram below. The 2 blocks now move to the right at a constant speed of 3 meters per second. 2.1 state Newton's first law of motion in words. I'm going to let you guys do that. And then 2.2, draw a level free body diagram for block P. That is for 5 marks. So because the question is for 5 marks, we do expect the number of forces on the free body diagram to be 5, right? So let's go ahead and see what we're going to end up with. So the first force that you should indicate when you have a free body, when you want to draw a free body diagram, should be the weight. If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. So we have the weight, too thick, if you ask me, too thick. Can't believe I just said that. But yes, we have the weight, we have the normal force. The surface is flat, so the normal force will look like that. And then we have the applied force. So this is force applied. The two blocks are connected by a light inextensible string. So we're gonna have the tension, and then we have frictional force. So frictional force, and that is the 5 marks for 2.2. What about 2.3? So 2.3 says calculate the magnitude of force F. The string connecting P and Q suddenly breaks while force F is still being applied. Oh, okay, no, this statement is for the follow-up question. 2.3 just says calculate the magnitude of force F. So because we have a free body diagram for block P of mass 5 kg, let's start by using that block, that free body diagram, to see if we can calculate the magnitude of force F. So we're going to start by saying F net is equals to MA. Obviously, the component of the applied force, which is pulling the object to the right, is the x component, right? So we're going to say F cos of theta minus the forces that are opposing. That is the tension force and the frictional force. That is all equals to MA. So the angle is 30 degrees, right? So we're going to have F cos of 30 minus the tension, which we do not have, minus the frictional force, which is said to be 2.5 for block P. So we have 2.5, and this is equals to MA. So the mass is 5, the acceleration is 0. Why is the acceleration 0? The object is moving at a constant velocity of 5, not of 5, but of 3 meters per second. It is written here. So when an object is moving at a constant velocity, at a constant speed, irregardless of the actual magnitude, the acceleration is 0. So what is cos 30? That is 0.866. So we have 0.866 F minus the tension minus 2.5 being equals to 0. Right, so we have two variables. We have the force, we have the tension. We cannot proceed. That's where we go to the 2 kg block. So the 2 kg block, we have to start with the free body diagram, right? We have the weight, obviously. We have the normal force. We have the tension. We have the frictional force. So this is going to be F net is equals to MA once more. The force, not the force, but yes, the force that is pulling the object is the tension. The force that is opposing is the frictional force, and this is equals to MA. So we have the tension minus the frictional force of block Q, which is 1 Newton. So the tension minus 1 is equals to 2 multiplied by 0, because it's also moving at a constant speed. So the tension is equals to 1 Newtons. So now that we have the tension, well, I don't know why that keeps on happening, but now that we have let me see if I can fix that. Now that we have the tension, right, now that we have the tension, we can be able to calculate the force. So we're gonna have 0.866 F minus 1 minus 2.5 being equals to 0. So 0.866 F is equals to 3.5. So what is 3.5 divided by the coefficient of the force? F is equals to 4.04 newtons. So there we go, we have the magnitude of force F. Okay, and then 2.4 is the direction of the acceleration of block Q. Oh well, we have to take a look at this statement first. The string connecting P and Q suddenly breaks while force F is still being applied. Is the direction of the acceleration of block Q now towards the left or right? Explain the answer. So here we have block Q, right? The string is now broken connecting the two blocks. So what do you expect ball Q to do? You expect it to come to a stop eventually, right? You expect it to slow down and come to a stop because it is no longer being pulled. So when it is slowing down, what is the direction of the acceleration? It's to the left. The direction of the acceleration is to the left because here, when the string breaks, it has a velocity of 3 meters per second. And when it comes to a stop, it has a velocity of 0 meters per second. So acceleration is equals to Vf minus Vi divided by the change in time. Vi is greater than Vf, so the acceleration is going to be negative, right? We're going to have minus 3 divided by delta t. Okay, so the acceleration is going to be to the left. And then 2.5, how will the net force acting on block P be affected? Choose from increase, decrease, or remain the same. Obviously, it's going to increase because now the only force that is acting on P, obviously the net force is going to increase because we no longer have the tension which was holding it back. Okay, so in 3.1.2, you might be tempted to use the conservation of linear momentum. That is not the correct approach to take. So let's take a look and see what is happening. So during a snooker game, two balls X and Y collide elastically. Ball X has a mass of 1.56 kilograms and travels at 3 meters per second in a straight line. Ball Y with an unknown mass was stationary before ball X hit it. After the collision, ball X becomes stationary and ball Y moves forward at 2 meters per second in a straight line. 3.1.1, we're supposed to define or explain what is meant by the term elastic collision. And then in 3.1.2, we're supposed to calculate the mass of ball Y by making use of energy principles. So as I was saying, the information that we have, you might be tempted to use the conservation of linear momentum. But because the equation itself is saying calculate the mass of ball Y by making use of energy principles, we cannot use the conservation of linear momentum. Because in using the conservation of linear momentum, there's no SI unit there that is joules. So it doesn't make sense to say use of energy principles and you use the conservation of linear momentum. So let's take a look at the information that we have and see which approach we need to take. So the first thing that we need to do, because we don't have a sketch, is to conceptualize, form our own sketch so that we can see what is happening with clarity. So ball X is traveling in a straight line at 3 meters per second, right? So let's go ahead and have that. So this is ball X traveling to the right with a speed of 3 meters per second. And then ball Y of an unknown mass is stationary. So let's have ball Y here, which is initially stationary. Right, it is then hit by ball X. Ball X now becomes stationary. So this is before the collision, and then this is after the collision. So let's take a look. Ball X now becomes stationary and ball Y moves forward with a speed of 2 meters per second. Right, so this is what is happening in this scenario. So we have the mass of Y, or the mass of X rather. Right, we have the mass of X, the mass of Y is unknown. And then after the collision, we will still have the mass of the mass of X obviously, and then the mass of Y would still be unknown. So using energy principles, so take a look at this. In 3.1.1, we defined an elastic collision, and then in the equation statement, we are told that two balls X and Y collide elastically. So we can use the conservation of kinetic energy. We can say that the sum of EK before is equals to the sum of the kinetic energy after the collision. Right, we are only able to do this because we are told that the collision between the two objects is elastic. So the kinetic energy of x before the collision is just half mv squared plus the kinetic energy of y. Still we have half mv squared. This is going to be equals to the kinetic energy of x after the collision, half mv squared plus the kinetic energy of y after the collision, which is half mv squared. So the kinetic energy of x before the collision is moving to the right with a velocity of 3 meters per second. Let's take direction to the right is positive. So we're going to have half, the mass is said to be 1.56, and then the velocity is 3 meters per second to the right. So we're going to have 3 squared plus the kinetic energy of y. It is initially stationary. So in place of the mass, we're going to have mass. But then in place of the velocity, we're going to have 0, and then we square that. If you like this video, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. That is going to be equals to a half the mass of x, which is 1.56. But after colliding with y, it becomes stationary. So we're going to have 0 squared plus a half the mass of y, which is m, and its velocity after the collision is 2 meters per second. We're told that it moves forward at a velocity of 2 meters per second in a straight line. So we're going to multiply that by 2 and we square that. Okay, so what is a half multiplied by 1.56 multiplied by 3 squared? Let me see. This is giving me 7.02. So we have 7.02 being equals to, obviously here we're multiplying by 0, so that just falls away. And then we have a half multiplied by m multiplied by 4. So 7.02 is equals to 2m. We divide both sides by 2, and then we get m is equals to 3.51 kilograms. So that is 3.1.2. We cannot use the conservation of momentum, the conservation of linear momentum, because the question says use energy principles. We have to use the conservation of kinetic energy. Let's take a look at 3.2. So 3.2. A car, car A fitted with crumple zones collides head-on with car B without crumple zones. Car A of mass 1,350 kilograms moves eastwards at 20 meters per second before colliding with car B of mass 1,500 kgs moving at 10 meters per second westward. Immediately after the collision, car A moves backwards at 5 meters per second. Right, and then we are told that friction can be ignored. And then a physics learner in grade 12 at the scene argues that car A's driver will be less injured compared to car B's driver because car A is fitted with crumple zones. Is the learner correct? Choose from yes or no. Right, obviously the learner is correct here, right? So the answer is yes. And then in 3.2.2, we're supposed to explain why that is the case. So what does a crumple zone do in a car? Well, let's start here. We know that F net is equals to delta P over delta T, Newton's second law in terms of momentum. So a crumple zone increases the contact time, right? The time of collision. So as delta T increases, it is easy to see that F net will decrease, right? So that is why it is safer to be in a car with a crumple zone. The crumple zone increases the collision time, and then according to Newton's second law of motion in terms of momentum, the net force is inversely proportional to the time of collision. So less force, less damage. That is 3.2.2. Let's take a look at 3.2.3. 3.2.3, we're supposed to state the principle of conservation of linear momentum in words. I'm going to let you do that, and I'm assuming in 3.2.4 we are going to have to use the conservation of linear momentum. So let's take a look. We're supposed to calculate the velocity of car B after the collision. Right, so it seems like the information that we're given leads us or allows us to use the conservation of linear momentum. So let's see where we end up with that. So the sum of the momentum before the collision should be equal to the sum of the momentum after the collision. So because we have two objects, we're gonna have m1 v1 plus m2 v2 being equals to m1 v1 plus m2 v2. You know, the subscripts are not really important in this case, yeah, as long as we substitute the correct things. Obviously we'll take direction to the right as positive, right? Well, the question is talking about eastwards and westward, so let me say we're going to take the direction to the east as positive. Okay, so car A has a mass of 1,350 kilograms, so that is 1,350 kilograms. It's moving eastwards at 20 meters per second, so that is going to be multiplied by 20, plus the momentum of car B. It has a mass of 1,500 kgs, and then it's moving westward with a speed of 10 meters per second. So that is multiplied by minus 10 because we're taking direction to the east as positive. And then after the collision, car A moves backward at 5 meters per second. So we're going to have 1,350 kgs multiplied by minus 5 plus 1,500 multiplied by v, right, the velocity of car B after the collision. So now we are at the end of the physics, right? We are just now solving for v, right? We have done all the physics work that we need to do. So I'm just substituting the left hand side on my calculator, and then I'm getting is this 12,000. I'm getting 12,000 is equals to, so 1,350 multiplied by minus 5, that is minus 6,750 plus 1,500 v. So I need to take 6,750 to the left hand side, so it's going to become positive, right? So let me just do that math. I'm getting 18,750 being equals to 1,500 v. So I'm going to divide both sides by 1,500 obviously, and then I'm getting minus 12.5 being equals to v, right? So this is 12 point, does the question say the velocity? Yes, it's the velocity, so we have to include the direction. So I'm getting 12.5 meters per second. I've taken direction to the east as positive. So now, because I'm getting a negative number, it means I should say westward. Westward is equals to v. Right, so that is 3.2.4. Let's take a look at question 4. So question 4, ball A is projected vertically upwards from the ground near a tall building with a speed of 24.5 meters per second. Ignore the effects of air friction. 4.1, I'm going to let you do that one. We're supposed to explain what is meant by the term projectile. And then 4.2, calculate the total time taken. Calculate the total time that ball A is in the air, right? Okay, so 4.2, it's a very basic question, right? It's one of the first things that we talk about under vertical projectile motion in my course, right? There's two ways in which we can answer this question. You should already know if you're inside the course, but if you're not, the link is on my bio. Go ahead and check that out. There's very interesting detailed videos about vertical projectile motion, electrostatics, organic chemistry, all the topics, right? Introduction videos. I tell you everything that you need to know. We don't just solve past exam questions, like very detailed introduction videos, because it doesn't make sense to solve past exam questions if you don't have the fundamentals, if you don't have the basics, right? Maybe you end up being able to calculate, but then those multiple choice questions that require you to understand the basics, you're not going to be able to do those questions. So let's take a look. 4.2. So one thing that we talk about, like I'm saying, is that let's say we have an object, right, and then it's projected, reaches some maximum height, and then goes down to strike the ground. Okay, so we talk about the fact that the time taken to go from where it is projected to maximum height is the same time taken to go from maximum height back to where it was projected, right? So that gives us one way to answer the question. Let me show you. We can say VF is equals to VI plus A delta T. At the maximum height, we know that the velocity is 0. So we're going to have 0. I'm taking up as positive. So VI is going to be 24.5 plus minus 9.8 delta T. So delta T is equals to minus 24.5 divided by minus 9.8, which is 2.5 seconds. So this is the time taken to grow from the time it is projected to the maximum height. But the same time taken to go from the time it is projected to maximum height is the same time taken to go from maximum height back to where it was projected. So we can say time taken is equals to 2.5 multiplied by 2, which is equals to 5 seconds. That is one approach. Another thing that we talk about is that the velocity at which it was projected, 24.5, is the same magnitude at which it will pass that same point on its way down. So here we are also going to have 24.5, but then it is now going down, right? So when we substitute that 24.5, we must put a minus sign, assuming we have taken up as positive. So take a look at this. The other way to answer this question, we would say that VF is equals to VI plus A delta T, right? So VF, now it is going downwards. We're going to have minus 24.5 being equals to VI, which is upwards, 24.5, plus the acceleration, minus 9.8 multiplied by delta T, right? So we have minus 24.5 minus 24.5, which is minus 49 is equals to minus 9.8 delta T. Delta T is equals to 5 seconds. So there we go. Those are the two ways that we can use to immediately answer that question. 4.2, right? Let's take a look at 4.3. Calculate the total distance traveled by ball A during the last second of its motion. Okay, so let's go back to the sketch and see what we can do. Right. Obviously, again, right, inside the course, we have talked about this kind of question. We've solved a question like this before. Yeah, so do check it out if you are yet to do so. I want to drag these things down. Maybe in some issues. Okay, it's not going to work. Let me just erase and take a look at the sketch and talk about this problem. Okay, so we're interested in the motion of the object or the distance traveled during the last second. Okay, so which approach can we take? So let's take a look at the motion of the object from maximum height to when it travels to strike the ground. Okay, obviously the initial velocity here, we know that it is 0, and the velocity at which is gonna strike the ground, we know that it is minus 24.5, right? Minus 24.5, and then we know that this journey, so to say, or that part of the motion takes 2.5 seconds. I'm trying to write here, but something's going wrong. Okay, there we go. It takes 2.5 seconds. So how can we calculate the distance traveled by the object in the last second? So there's two things we can do. We can calculate the velocity before 1 second before, well, it strikes the ground, right? and then we would be able to calculate the distance traveled by the object in the last second. Let me show you what I'm talking about. Okay, so we have this velocity at which it strikes the ground of minus 24.5. But what was the velocity of the object 1 second before it was 24.5? The velocity was 24.5 minus 9.8, which is 14.7. So the velocity 1 second before striking the ground is 14.7 meters per second. How do we know that? Again, the introduction video on vertical projectile motion. We can go through the entire thing again, right? But just click the link on my bio. Get the course. It's free for 7 days. You don't have to worry about paying anything, and then you'll understand why I'm saying so. So now that we have VI 1 second before striking the ground and VF, it should be easy to find delta Y. Okay, so let me show you how we can do that. I'm just gonna erase this. We have delta T also, because we know that this takes 1 second, right? So can we just say delta Y is equals to VI delta T plus a half acceleration delta T squared? Can we just do that instead? You know, this will work. So we're gonna have VI, which is minus 14.7. Delta T is 1, obviously, plus a half, and then minus 9.8. Delta T is 1, we square that. And then now it's just a matter of putting that in my calculator. Right. So what am I getting? Let me see. I'm getting 19.6 meters. Okay, let's proceed. 4.4. Once again, after ball A is projected upwards, ball B is also projected vertically upwards, but from the roof of the building. The roof is 56 meters above the ground. Both balls reach the ground at the same instant. Ignore the effects of a friction. 4.4.1. Calculate the speed at which ball B is projected upwards from the roof. Okay, ball B strikes the ground at the same instant as ball A. Okay, so the first thing that we need to understand here, the time taken by ball A to strike the ground, as we calculated before, is 5 seconds. But ball B is projected 1 second later, but it strikes the ground at the same instant as ball A. So the time taken by as ball B. So the time taken by ball A, by ball B, right? It should be 5 minus 1, right? Because it is projected 1 second later, but strikes the ground at the same time with ball A. So the time taken by ball B should be 5 minus 1, which is 4 seconds, right? It only starts its motion 1 second after, but strikes the ground at the same instant. So it took 4 seconds to travel. Okay, so that is the time taken by ball B. We know the displacement should be 56 meters, right, downwards. So we have delta T, we have delta Y. Obviously, we know the acceleration. We are looking for VI. This will be quite easy to do because we have 4 variables, only one is unknown. Let's see. We can say that delta Y is equals to VI delta T plus a half acceleration delta T squared. So the displacement minus 56 is equals to VI. That's what we're interested in. The time is 4 seconds plus a half. The acceleration is minus 9.8. The time, as I've said, is 4 seconds, and we square that. So we're going to have minus 56 being equals to 4 VI. And then let me just put that in my calculator. A half multiplied by minus 9.8 multiplied by 4 squared, 78.4. So we have minus 78.4. So minus 56 plus 78.4, that is 22.4. So 22.4 is equals to 4 VI. Obviously, we just divide both sides by 4, and we get 5.6. So this is 5.6 meters per second. Oh, well, we don't have to give the direction because it says the speed. But, right, that is the speed. 4.4.2, calculate the speed at which ball B reaches the ground. Now we are looking for VF. We have VI and delta T, so that should be quite easy to calculate. We can say that VF is equals to VI plus A delta T. So VF is going to be equals to VI, which is 5.6, plus the acceleration minus 9.8. Delta T is 4 seconds. So let me put that in my calculator. 5.6 plus minus 9.8 multiplied by 4 minus 33.6. The question says the speed, so let's just say 33.6 meters per second and not worry about the direction. Okay, 4.4.2. Let's take a look at 4.5. 4.5, sketch velocity time graphs for both for the motion of both balls on the same set of axes. Clearly label the graphs for A and B indicate the following on the graphs. Okay, so let's go ahead and see the y-axis and the x-axis. Okay, so the y-axis, that is velocity in meters per second, and the x-axis is time in seconds. Okay, so the initial velocity of ball A is 24.5. So let's say 24.5 is somewhere here, 24.5. And then strikes the ground with a velocity of minus 24.5. I'm still taking up its positive here. And then how much time does it take to reach the maximum height? It takes 2.5 seconds. So this is 2.5 seconds. Or let me just draw the graph first, and I'm gonna write those values after. Okay, so let me just see which color to use now. Let's use that. So that is the velocity time graph for ball A. Okay, and then let's move to B, right? Let's have some values for B. So B, the initial velocity is 5.6. So we have 5.6 should be somewhere here. That's where we should have 5.6. And then clearly it strikes the ground with a velocity of 33.6. So minus 33.6 has to be somewhere here, right? So it strikes the ground there. Okay, but it is only projected 1 second later. So let's say this is 2.5. Obviously this is 5. So 1 has to be somewhere here. So that's where the graph of our object B has to start. So let's just change the color to green, maybe, and then it is projected upwards. So from 5.6. Okay, let me just erase this one because now I can't draw it the way I want. So from 5.6 reaches maximum height and then goes to strike the ground. Yeah, I'm trying to make this as good as I possibly can. Okay, I think I got it there. So there we go. We strike the ground at that point. Let me go back to red and fill in the values. So here we have 1. We have 1 here. That is 1 second. 1 second. Okay, so this is for A and this is for B. Right, I think we have all that we need there. So there we go. That is the velocity time graph for A. If you like this video, B, you will definitely love my course. Go ahead and click the link on my bio and you will land on this page. You will not only find the past exam questions, but introduction videos where I break down complex concepts into small pieces that are easy to digest. It is very important in grade 12 to stay ahead of your teacher, and this is what this course is for. It's very easy to navigate through the course as videos are arranged into collections. You can clearly see that we have electrostatics, work energy and power, Doppler effect, so on and so on. Do you maybe need help with study tips and creating your own timetable? We can talk about that inside the course and I can help you out. It doesn't even take a minute to join. Can't wait to hear from you. Use the information in the table to answer the questions that follow. 5.1, 5.1.1. For compound D, write down the homologous series to which it belongs. So let's go ahead and take a look. When you take a look at compound D, the IUPAC name pentane 2-one. It should be quite obvious that the homologous series is ketones, right? So that is the answer to 5.1.1. And then 5.1.2, IUPAC name of a functional isomer. The functional isomer to a ketone should be an aldehyde. The functional isomer to an ester should be a carboxylic acid, right? Those are the two pairs of functional isomers that we have. So because these ketone, that is compound D, has 5 carbons, the functional isomer is any aldehyde with 5 carbons, of which the most obvious answer should be pentanal. So the answer to 5.1.2 is pentanal. Obviously, you can have other aldehydes with 5 carbons that are not pentanal. For instance, 2-methyl-butanol would also be a functional isomer to pentane 2-one. But the obvious answer should be pentanal. That is 5.1.2. And then 5.2.1, we're looking for the IUPAC name of compound A. So let's go ahead and take a look. Compound A is a haloalkane, right? And then in naming haloalkanes, we don't have some distinct functional group, right? We just need to identify our longest chain and start numbering our carbons from the side that leads to the smallest number. Let me show you what I'm talking about. So first things first, we're looking for the longest carbon chain. So let's take a look. 1, 2, 3, 4, 5, 6, right? And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So it looks like the straight chain 1, 2, 3, 4, 5, 6 is our longest carbon chain. So let's take that as our longest carbon chain. So where do we start numbering our carbons? From the left hand side or from the right hand side? Let's take a look. If we start numbering from the left hand side, we're going to have a branch on the second carbon, on the third, and on the 5th carbon. So when we add all those numbers, when we name from the left, we start numbering our carbons from the left, the total is going to be 10, right? And then let's take a look at what happens when we start naming from the right. We're going to have a branch on the second carbon, on the 4th, and then on carbon number 5, we are also going to have a branch, right? So when we start numbering from the right, we end up with 5, 4, 2, which is 11. So clearly we have to start numbering from the left because that's the way, or that's, the side that leads to the smallest number. So let's go ahead and do that. We have to start numbering from the left. So we have a branch on the second, like we have established. Let me see if we can, on the second, on the third, and on the 5th. So there we go. So we have 2.3-dimethyl, right? And 5 bromo. But we have to arrange the substituents in alphabetical order. So we are actually going to have 5 bromo hyphen 2.3-dimethyl hexane. Okay, there we go. That is the IUPAC name of this haloalkane. If there's still some confusion, I know this confuses a lot of people. Believe me, the IUPAC name of haloalkanes confuses a lot of people. I have an entire video dedicated to just naming haloalkanes. I think that video is like 10-12 minutes long, right? I'm going to teach you everything, from the first step to the last. You're never going to get the naming of haloalkanes wrong after you go through that video. Just, click the link on my bio and go to the organic chemistry collections and you'll get that video. Okay, that is 5.2.1. Let's take a look at 5.2.2. We're supposed to write down the structural formula of compound E, which is 4-methyl pent-2YNE. So pent, we need 5 carbons, right? So we're gonna have 5.2.2 pent 1, 2, 3, 4, 5. And then on the second carbon we have a triple bond, hence pent-2YNE. So this is where we have the triple bond. And then on the fourth we have a branch. So we have a branch right here. So there we go. That is the structural formula of compound E. Okay, but you gotta make sure that you have the right number of bonds. You don't exceed. So this carbon has 1, 2, 3, 4 bonds. Everything is fine. And then these two, they have 1, 2, 3, 4. 1, 2, 3, 4. Okay, seems like all is well. Let's take a look at this one. 1, 2, 3. So we need a hydrogen there. Okay, so there we go. That is the structural formula of compound E. 5.3. Compound B is a primary alcohol, C3H8O. Okay, right. And then write down the name of the meaning of the term primary alcohol. Well, the carbon atom that is bonded to the hydroxyl group is bonded to one other carbon. That is primary alcohol. And then in secondary, it will be bonded to 2. And then in tertiary, it will be bonded to 3. And then 5.3.2. Compound B reacts with another organic compound X to form compound C. So compound C is an ester, right? So we already know that compound X should be a organic, well, a carboxylic acid. So write down the name of reaction, the type of reaction that takes place. So it is esterification. And then identify or IUPAC name of compound X. So take a look at this. This part where we have a oxygen with a single bond, right, is coming from the alcohol, and then the other part comes from the acid. So the acid that was used to form this compound C has 4 carbons, 1, 2, 3, 4. So obviously the answer here should be butanoic acid. So butanoic acid is the answer to 5.3.2. So butanoic acid. There we go. And then anything else? No, actually, let's go to question 6. Right. Question 6. The melting points and the boiling points of fostering straight chain alkanes are shown in the table below. Write down the predominant phase of the following alkanes at minus 100 degrees Celsius. Choose from gas, liquid, or solid. 6.1.1 pentane. So let's take a look at pentane. The temperature which we're interested in is minus 100 degrees Celsius. So at minus 100 degrees Celsius, it has already melted because it melts at minus 130. But it is yet to boil because it boils at 36.1. So the temperature is between the melting point and the boiling point. So the substance should be a liquid when the temperature is between the boiling point and the melting point. And then 6.1.2 octane. The melting point of octane is minus 57 and the boiling point is 125. So minus 100 degrees Celsius is less than minus 57. So the substance has not yet melted. So it means that the phase should be solid, right? If the temperature is less than the melting point, it is solid. If it is greater than the boiling point, it is gas. If it is in between, it is liquid. Okay. 6.2.1 hexane is now compared to 2.2 dimethyl butane. 6.2.1 define the term boiling point. I'm going to let you do that. And then 6.2.2 is the boiling point of 2.2 dimethyl butane higher than, lower than, or equal to that of hexane. The boiling point of 2.2 dimethyl butane should be lower than compared to that of hexane. And then what is the reason for that? Well, 2.2 dash dimethyl butane is more branched, right? It's more spherical, so it's going to have a smaller surface area. And then in having a smaller surface area, it is going to have weaker intermolecular forces. less energy is required, less boiling point, melting point, and then a higher vapor pressure, that is 6.2.3. Right. So when we are comparing 2.2 dimethylbutane and hexane, I like it to be in terms of branching, not in terms of chain length, even though it is accepted, right? You can say, oh, hexane has a longer chain length. It is going to be accepted, but I prefer it to be in terms of branching. Let's talk about chain length when we have pentane and butane, and say, oh, pentane is a higher boiling point because of longer chain length. But then when it is branching, let's keep it at branching and not chain length. Well, that's preference. Question 7, let's take a look. This is a question that quite easy, nothing complicated. There's a technique that we use to actually answer this question. Okay, write down the name of the type of reaction represented by the letters A and B, right? So let's take a look at A. So A, we have an alkene, right? We have an alkene which ends up being an alcohol. So what happened there? Obviously H2O was added, right? Hydrogen and OH, hence we have an alcohol. So it is an addition reaction. But what is the name of the type of reaction represented by the letters? I'm going with hydration. So 7.1.1, we have hydration. And then let's take a look at B. We start with an alkene, we end up with bromoethane. So obviously HBr was added. So that is hydrohalogenation. So 7.1.2, hydrohalogenation. There we go. And then 7.2, apart from the alkene, another reactant and a catalyst are needed in reaction A. Write down the name or formula of the other reactant. So the other reaction that is needed obviously is H2O, like we've talked about. So that is another reactant. So H2O. And then the catalyst that is needed, dilute sulfuric acid. So we need H2SO for hydration to take place. Then the last question, 7.3, use structural formula to write down a balanced chemical equation for reaction B. So that is quite an easy one. So we shouldn't spend a lot of time on this question. So plus HBr, we have a hyphen there to indicate the bond. HBr is not one thing. And then the answer, right, bromoethane. There we go.